In today's session, we will talk about Kirchoff laws, which are very helpful to solve a network. Solving a network means finding the current flowing through various branches. We will also learn what is meant by star network and delta network and the conversions between them. Kirchoff laws. Let us see how many types of laws we have. In Kirchoff's we have two types of laws. They are Kirchoff's current law or KCL, Kirchoff's voltage law or KVL. Let us see the first law. This law relates to the current at the junction point of a circuit. We know that at a junction currents enter in from one line and leave into another line. It is just like a traffic at a crossroads. Let us see first of all what is Kirchoff's current law. What does it state? The algebraic sum of all the currents meeting at a point or junction in a network is 0. Here we need to stress the word algebraic. What do you mean by algebraic? Algebraic takes care of the current direction that we are talking of. If the current is flowing towards the junction, it is taken positive. If it is flowing away from a junction, it is taken negative. Let us consider 5 conductors carrying currents I1, I2, I3, I4 and I5. As we said earlier, we have to bother about the current directions. If it is towards the junction, it has to be taken positive. If it is away from the junction, it has to be taken negative. If we observe the currents, they come and they leave. The currents that are flowing towards the junction should be taken as positive and the leaving must be taken as negative. So, we can state this equation as I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. As we can see, both I1 and I2 are closing towards the junction, whereas I3, I4 and I5 are moving away from the junction. That is why we have taken it as a negative. So, the entire algebraic sum is equal to 0. The same Kirchoff laws can be stated in another way, that is, in LA electrical network, the sum of incoming currents is equal to sum of outgoing currents, isn't it? If we observe, I1 and I2 is coming, whereas I3, I4 and I5 are leaving. So, we can put down the equation as I1 plus I2 is equal to I3 plus I4 plus I5. This is about the Kirchoff's current law. Now, let us talk about the Kirchoff second law or Kirchoff's voltage law. This law relates the EMFs and voltage drops in a circuit. First of all, let us see what do we mean by an EMF source. A battery or a generator would act as an EMF source. Let us see what do you mean by a voltage drop. When a current flows through a resistor, a drop of voltage takes place across it. This drop we call it as a voltage drop, which is given by I into R. Now, knowing this information, let us see what KVL states. In any closed circuit or mesh, the algebraic sum of all the electromotive forces and the voltage drops is equal to 0. That means, sigma EMFs plus sigma I into R is equal to 0. The total sum of EMFs and the total sum of drops that is taking place in the circuit is equal to 0. Before going any further, let us see about the sign conventions for EMF. If we consider the circuit, these are the EMF sources, positive as well as negative terminals. If we are considering the circuit from the positive terminal to the negative terminal, there is a fall in potential. A fall in potential is represented by a negative sign, that is minus E. If we take the other case, that is if we are coming from negative terminal towards the positive terminal, then there is a rise in potential, that is it is taken as a positive E, or a positive sign is given. On the other hand, if we talk about the resistors, the voltage drop across the resistors, if we say whenever current enters the resistance, it is marked as a positive sign. From where the current is leaving, it is marked as a negative sign. In such a case, if we are considering it from in this direction, that is coming from positive to negative, as we have seen earlier, it is a fall in potential, that is negative, which is minus IR. Likewise, if we take the current, mark the positive and negative, the current, if we are considering it from the other way, that is from negative terminal to the positive terminal, then it is a rise in potential, which is plus IR. Knowing these basic things, let us apply them to a circuit to find currents in various branches. Consider a circuit having two EMF sources, E1 and E2, and has got resistances R1 and R2. The currents that we are assuming are I1, I2, and I1 plus I2 is flowing through the resistance R1. The direction of current is not important. If it is wrong, it would be indicated by a negative sign in the result. Later, now we have got to write down the loop equations. Before that, let us see, we have to mark the positive as well as the negative signs. If we observe, the current is entering R1 from the top side. So, we have indicated with a positive sign, and when the current is leaving, it is indicated with a negative sign. Similarly, if we observe across R2, the current I2, it enters from the bottom, it is a positive one, from the top it is leaving, it is a negative. Mark the terminals, then we can write down the equations. If we consider the loop ABCFA, that is, we can write down the equation. Let us try writing down. From A to B, we have got the source E1. Let us consider the direction of the loop like this, that is from A, B, C, F and A. From A to B, we have got the source, that is E1. We are moving in this direction from A to B, that is from negative sign to positive sign. So, we have got a rise in potential, which is indicated by a positive sign, that is I can write down it is E1. Next, while moving from B to C, we have got no component. Coming from C to F, we have got R1, the currents being I1 plus I2. If you observe, we are moving from positive to negative terminal, that is there is a fall in potential. So, we have to take a negative sign. So, we have got minus of I1 plus I2 into R1, whereas in FA we have got no component. So, this is equated to 0. Similarly, we shall write down the next loop equation.
Start, sir.
Let us look at the loop C D E F C. C to D we have got no component, from D to E we have got R2, that is we are moving from minus to positive, that is a rise in potential. So, we have got I2 R2, from E to F we have got, we are moving from positive to negative, which is a fall in potential indicated as minus E2. From F to C we have got a rise in potential, isn't it? We are moving from a negative towards the positive. So, we have got plus I1 I2 into R1. Now, let us write down the other loop equation, that is loop A, B, C, D, E, F and A. We have got the equation as E1 plus I2 R2 minus E2 is equal to 0. From A to B we have got E1, we are moving from negative to positive. So, what it should be? It should be a positive sign, isn't it? From B to D we have got no components. From D to E we have got R2, that is we are moving from a negative to positive. So, we have got plus I2 R2, and from E to F we have got a negative sign, as there is a fall in potential, because we have got positive towards the negative, isn't it? So, these are the loop equations we can write down. With the help of these equations we can solve and get the currents I1 and I2. Now, let us solve one problem based upon the same equations and the circuit. If we are considering the circuit, if E1 is 35 volts, E2 is 40 volts, R1 is 5 ohms, R2 is 4 ohms, then we are supposed to find out the currents I1 and I2. We have seen the loop equation ABCFA, which is equal to E1 minus I1 plus I2 into R1, as well as the loop equation ABCDEF and A to be E1 plus I2 R2 minus E2 is equal to 0. Now, we will put down E1 as 35, E2 40, R1 5, R2 4. Substitute this in the equations, that is 35 minus I1 plus I2 into 5 is equal to 0, and 35 plus I2 into 4 minus 40. We will have this equation as I2 plus 4 minus 5 is equal to 0. Likewise, we can get I2 is equal to 1.25. Substitute this I2 in this equation, then we get 5 I1 plus 5 into 1.25 is equal to 35. So, we will end up getting I1 as 5.75. So, we have solved the problem and we have obtained the currents I1 and I2, I1 being 5.75 amps, I2 being 1.25 amps. Likewise, we can write down any circuit can be written down into number of equations and can be solved. If the equations or if the unknowns are more than 3, then we have to go for solving the network by using matrix methods. Let us look into a star connection, star or Y configuration. A star connection is one in which similar ends of 3 elements are connected to a common point. Let us consider the 3 elements to be R1, R2 and R3, the terminals A and B. Now, as we have said, the similar ends must be connected, that is either we can connect all the A ends or either we can connect all the B ends. Now, let us make the connection. We are connected all the B ends. So, the same is we see these 3 are shorted, is not it. So, we can put down the same figure like this, is not it. All the terminals are brought and connected to a common point which is known as N. The same figure can be redrawn like this. This would be a T symbol, is not it. We have got all the things A, R1, R2, R3, is not it. All the B terminals are brought down and connected to a one point N. The same can be redrawn once again like this, indicating as a Y, is not it, that is R1, R2 and R3. Now, this is how we make a star connection, that is all the similar ends are connected to a single point which is N. Let us look into the delta or mesh configuration. In delta or mesh configuration, the dissimilar ends of the 3 elements are connected together, that is we have 3 elements. Now, we shall make the connections. The B is connected to A, once again the B of the second element is connected to A of the third element. Likewise, we have the third element is connected to the first element. This can be redrawn like this, stating 1, 2 and 3 would be the terminals. If you observe, A is connected to B, A is connected to B and A is connected to B. All the dissimilar ends are connected. The same figure can be redrawn. If you observe, we have got the terminals 1 and 2 and 3. If you observe, the resistance has been renamed as R12, indicating that this resistance is connected between the terminals 1 and 2. Likewise, the others R23 and R31. This can once again be redrawn into this format, that is 1 and 2 and 3 terminals. R12 means connected between 1 and 2, R23 connected between 2 and 3, R31 connected between 3 and 1. Likewise, we can check out the delta connection. Now, we came through knowing a star connection as well as a delta connection. Let us look how to convert the star or delta into the other one. First of all, let us focus upon converting a delta or star delta network into a star. If we have got a delta network with the terminals A, B and C, resistances being RAB, RBC and RCA, if you want this to be converted into an equivalent star network comprising of RA, RB and RC, then we have to follow a condition. That condition being the resistance between any two terminals must be same. That is, if we consider the resistance between A and B, this resistance must be equal to the resistance that comes across A and B of star network. So, let us go forward and see how are we going to do this. If we look, if we take the first case, let us consider the resistance that is coming between RAB, that is A and B, as well as RA and RB. We have got the resistance in star network is between terminals A and B being RA and RB. The RC is kept open, so that is not in the circuit. So, we have got these two in series, which is represented by RA plus RB. If you look at the delta configuration, in RA in across A and B terminal, we have got RAB as well as we have got RCA and RBC. These two are connected in series. This terminal is kept open, that is there is no connection. So, these two come in series. So, which is represented by RCA plus RBC. This combination is in parallel with RAB. So, we have got RA plus RB is equal to RAB in parallel with RCA plus RBC. Likewise, we can write down for the other parts. Let us indicate this one with a one equation. We can write down for BC. Between BC we have got RB plus RC. Here we have got RBC in parallel with RAB plus RCA. Likewise, we have got the other equation. Let us write down this as the second equation. We have got the other equation, that is RC and RA is equal to RCA in parallel with RAB plus RBC. Let us indicate this as the third equation. Now, by solving the three equations, we will get RA is equal to RCA into RAB by RAB plus RBC plus RCA. That is, we are able to obtain a star element from the delta configuration. If you observe, RA is equal to RAB into RCA divided by RAB plus RBC plus RCA. Likewise, we have got the others, that is RB is equal to RBC into RAB divided by RAB plus RBC plus RCA. Let this be equation number 5. Likewise, we have got RC equal to RCA into RBC divided by RAB plus RBC plus RCA, that is a sum of all the delta elements. Let this be indicated by the equation number 6. This is how we are going to convert a delta network into star. Let us look at a generalized one, that is, if we have got the delta configuration, we want to have a star. So, this we can put it down as any arm of star connection can be obtained by product of two adjacent arms of delta divided by sum of arms of delta. That is, for example, say if you want RA, then it is a product of adjacent arms RAB into RCA divided by the sum of the arms of delta, that is RAB plus RBC plus RCA. This is how we are going to convert a delta network into a star. Let us go to convert a star network into a delta network. If you have got a star given with the three elements RA, RB and RC, we want to find out the corresponding delta network indicated by the RAB, RBC and RCA. Now, multiplying previous equations 4 and 5, 5 and 6, 6 and 4 and with suitable modifications, we will be able to obtain RAB is equal to, that is RAB is equal to RA RB plus RB RC plus RC RA divided by, we want RAB. What is opposite to RAB? You have got RC. So, it is divided by RC. Similarly, if you want for RBC, we have got RARB, RBRC, RCRA divided by RBC. The opposite component would be RA. It is an RA. Likewise, we can have for RCA. RCA is equal to RARB, RBRC, RCRA divided by RCA, opposite component would be RB. So, this is how we can have the equivalent delta from the given star. Let us generalize this one. If given the star network, we want to find out the equivalent delta. The equivalent delta can be obtained like this: RAB, RBC and RCA, that is any arm of delta connection is equal to sigma RA RB, indicating that we have to multiply RA RB plus RB RC plus RC RA divided by opposite star arm. That is, if we are considering RAB, we have to take the opposite star arm, means we have to take opposite to this one, that is RC, we have to take RC. If we are considering RBC, we have to take RA, if it is RCA, it has to be RB. Now, let us solve some problems of the conversions. Convert the given star network to equivalent delta network. Star RA, RB and RC, if we have got the resistances as 1, 2 and 3, we are supposed to find the equivalent delta network. We know the formulas, that is RAB is equal to RARB plus RBRC plus RC and RA divided by, it is RC. RA means opposite arm is RC. So, let us put down the values: 1 into 2, 2 into 3 plus 3 into 4 divided by, what should it come? It is 3. So, we will end up getting the value as 11 by 3 ohms. Likewise, we can find for RBC as well. RBC is equal to 11 by 1 ohm. We know this component is common for all the elements. The bottom one, the denominator is changing. For RBC, it has to be RA. RA is 1. So, it is 11 by 1 ohms. Likewise, we have got RCA is equal to 11 by 2. RCA opposite arm is RB, which is 2 ohms, that is 11 by 2 ohms. Now, let us convert a given delta network into a star network. If I have got RAB as 1 ohm, RBC 2, RCA as 3, we want to find out an equivalent star network, which can be found by RA is equal to RAB into RCA divided by RAB plus RBC plus RCA, is not it? If you want RA, adjacent arms RAB, RCA divided by sum of all the arms. Let us put on the values and solve. RAB into RCA, that is 3 into 1 divided by 1 plus 2 plus 3, which comes to 1 by 2, that is 3 by 6, which is 1 by 2 ohms. Likewise, we can find out for RB as well. RB is equal to 1 into 2 RB. What do you mean by RB? RB is this, means we have to multiply RAB and RBC, 1 into 2 by the total sum, which is 6, which comes to 1 by 3 ohms. Likewise, RC is equal to RC, we want RC, RC is equal to 2 into 3 divided by 6, which is equal to 1 ohm. By now, you have acquired the knowledge of how to solve a network with the help of KCL and KVL. Before applying Kirchoff laws to a network, first see whether the network can be simplified by star delta transformation. Be careful at the time of conversation. Try solving many number of problems so as to gain confidence. All the best.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040 322 0546.